let's compute the expected value of a geometric random variable. So suppose x is geometrically distributed with probability of success p. So by definition, the expected value of x is the following summation. Summation over the support of x. Support for a geometric random variable is 1 to infinity, of the probability mass function, or probability that big X equals little x, multiplied by little x. So remember, the probability mass function for a geometric random variable is 1 minus the probability of success to the x minus first power. You have to have x minus 1 failures first. And then multiplied by p, because you finally get a success on the xth trial. And then we still have multiplied by x from before. Then we're summing over our support. Okay, so one thing I'm going to do is I'm going to change 1 minus p to q. And I'm also going to pull this p outside the summation, because it does not depend on x, so it does not need to be inside the summation there. Okay, so that's going to make things look a little bit nicer. So we're going to have q to the x minus 1. And I'm also going to put that x in front of the q. So the reason I'm doing that is because now this thing inside the summation looks kind of like a derivative. It looks like you used the power rule on a function of q. And actually, you did. It's a little bit confusing here because x is not your variable. X is sort of just like an unknown number. So what you want to do is write summation derivative with respect to q, not x, of q to the xth power. Summation over the support, x equals 1 to infinity. All right, well, since the derivative is a linear operator, you can pull it outside the summation, and you can get this. Get p times the derivative with respect to q of the summation x equals 1 to infinity of q to the x. Now, you're going to see why this is called a geometric distribution here. Because this right here, this is a geometric series. So, if q is less than 1 in absolute value, which it must be because it's 1 minus a probability, then that summation is equal to q to the first power over 1 minus q. And then we still have the p and then the derivative. All right, well, we can use the quotient rule to take the derivative of this with respect to q, and we will get the derivative of the top, which is 1, times the bottom, which is 1 minus q, minus the derivative of the bottom, which is negative 1, times the top, which is q, which you're actually going to have plus q, over the bottom squared. Well, the top simplifies to just 1 And if we bring the p in, we just get p. So you get p over 1 minus q squared. Well, 1 minus q is p. So it's p over p squared, which is simply equal to 1 over p. And that is the expected value of a geometric random variable. And now you might know why it's called a geometric distribution.